Welcome back to the deep dive. Today, we are getting really granular, looking at a choice that gets made, hundreds of times a day on every shop floor.
Oh, easily. And it's a big one.
It's the choice between hard and soft check jaws in CNC machining. And, this isn't just a small preference. If you choose the wrong one, you can instantly scrap your part. We're talking real money and lost time.
It is the ultimate foundational decision.
Yeah.
I mean, machining begins and ends with how you hold the part. If your work holding fails, literally nothing else you do matters.
Absolutely. So our mission for this deep dive is to get to the core rule of thumb. Let's just state it right up front.
Okay.
You use hard jaws for roughing raw stock. That's when you need that maximum non-negotiable clamping force. And you switch to soft jaws for finishing, for delicate parts, or anything with a weird irregular shape. That's the only way you're going to get high concentricity and not mar the surface.
That's the perfect shop floor rule. It works 99% of the times.
Yeah.
But for a deep dive, we got to go deeper. Right. What's fascinating here is that the real difference isn't just, the serrated teeth versus a smooth face. It's deep in the material composition, the heat treatment. It's about how that chemistry changes the physics of the grip.
Okay, let's unpack that then. The material secret. Toughness versus gentleness. This is what defines everything. It's the reason you either leave deep bite marks or you get a mirror finish.
And we have to start with composition because it's a zero-sum game. When you optimize for one thing, like toughness, you automatically sacrifice something else.
In this case, machinability.
Exactly, machinability.
So let's start with the champion of toughness. Hard jaws. These things are built for just immense repetitive abuse.
They are, and they're typically made from a high-strength alloy or a carbon tool steel. This is not mild steel. This is serious metallurgy.
And it's not just the material itself, it's what's done to it. It's prepared.
Precisely. It's prepared through a really rigorous process. It's often through hardened, which means it's heat-treated through the entire structure, not just case-hardened on the surface.
And that process gets you a number on the Rockwell C scale, a really high number.
A very high number. You're typically looking at something that exceeds 48 HRC, and it often gets up to 55, 60, I've even seen 62 HRC.
And why is that specific number so critical? What does that hardness actually do?
Well, that hardness is what allows the jaw to do its main job. Bite into raw material without wearing itself out. If the jaws were softer than that, the abrasive, scaly surface of raw stock would just flatten those serrations in no time.
So they'd be useless after a few cycles.
Completely. That level of hardness lets the teeth penetrate the stock without collapsing. They're built for wear resistance.
Okay, so that's the tough guy. Now let's flip the script to soft jaws. We're prioritizing something totally different.
Totally different. Here, the number one priority is machinability. The most common material you'll see is 45 tag steel.
Which, for anyone who doesn't know that grade, is basically a medium carbon steel that hasn't been hardened.
Right. It's chosen because it's stable, it's pretty cheap, and crucially, you can cut it easily with standard tools right there in the machine.
That machinability is its superpower. But what if even that is too hard for the part you're holding?
Then you get into the really specialized stuff. For maximum delicacy, say you're holding a finished aerospace aluminum part or a thin-walled brass fitting. You'd use jaws made of aluminum, copper, or even brass.
So the jaw's much softer than the workpiece.
Has to be. That way, if there's any pressure, the jaw material gives way before the expensive finished surface of your part does. It's insurance.
Okay, so if we connect this all back to the bigger picture, hard jaws are hardened steel over 48 HRC, built for maximum abuse of the jaw.
Yeah.
And soft jaws are unhardened materials under 47 HRC, built for maximum machinability and zero damage to the part.
That's it. And that structural difference is what leads us right into how they're used in the shop floor.
That's a perfect transition. Let's get into our next section. Hard jaws as the default for, let's call it, brute force roughing. Why are they so mandatory for that first operation?
It really comes down to two things: safety and power transmission. When you start with raw stock, piece of scaly, hot-rolled steel, you need an absolutely unyielding grip.
Because roughing is aggressive. You're taking deep cuts, high feed rates.
You're generating huge cutting forces, massive amounts of torque. If that hold is weak, the part doesn't just slip and ruin the cut.
No, it can get ripped right out of the chuck. I mean, that's a catastrophic failure. You could damage the machine, the tooling.
It's incredibly dangerous.
Yeah.
And the feature that prevents this is the serration. Hard jaws aren't smooth. They have these sharp, toothed surfaces.
Here's where it gets really interesting for me. Those serrations, plus the massive clamping force from the chuck, they're designed to literally dig into the rough surface of the material.
It creates a powerful mechanical lock. You can think of it like a micro weld created by pure pressure. And because those teeth are hardened steel, they can take that pressure without flattening out,
And that lock is what lets you transmit all the torque from the spindle into the part.
without any slippage. That's the key. You can just push the machine hard. Deep cuts, fast feeds, all the things you need to do to get material off quickly. They are absolutely a tool for abuse, not for finesse.
And that toughness translates to efficiency, right? They resist all the vibration and pressure.
They handle countless clamping cycles on that rough, abrasive material without deforming themselves.
Which goes back to cost effectiveness. They're standardized, you buy them off the shelf, bolt them on, and go. There's zero setup time for just running bar stock.
For high-volume production, that's a huge economic advantage. Less downtime, less fuss.
But there is a trade-off there with that brute force grip.
There always is. While that lock is powerful, those serrations are creating stress risers. You're intentionally deforming the material in 3 spots. On a really delicate part, that could actually cause some distortion before you even get to finishing.
That's a great point. They solve the slipping problem, but they introduce a stress problem. So they're really only for that brutal stage of roughing where you just need to hog out material.
Exactly. If the part is a big solid chunk, hard jaws are your best friend. If it's thin-walled or complex, that's when they become a liability.
And that idea of liability brings us perfectly to our third section. Let's pivot to the complete opposite. Soft jaws. This is all about precision, versatility, and protecting the part.
Yeah, now we're talking about finishing passes, delicate components, and the big one, holding irregular shapes. Things like castings or forgings.
Because hard jaws really only work well on round or hex stock.
Right. You try to hold a weirdly shaped casting with hard jaws, it's just not going to work. Soft jaws are like the custom tailors of work holding.
The magic is that you machine them yourself. You mount a blank set of soft jaws.
Those unhardened steel blanks, yeah.
And you machine them in place on the machine you're going to use.
This process is usually called boring the jaws. You bore them to a perfect diameter, or you can mill a pocket or cut a complex profile that just perfectly cradles the part.
This gives you 2 huge benefits. The first is obvious. You can hold almost any shape.
Right? Got a weird contour on a casting. Just machine the negative of it into the jaw.
But the second benefit is precision. Let's talk about concentricity.
This is the big one. When you machine the jaws in place, you are making the clamping surface perfectly true to the machine's spindle center line. You eliminate almost all of that stacked up error.
Which is critical for second operations, where you need runout to be in the thousandths or even tenths of a thou.
It's the only way to guarantee it. But there's a nuance to boring jaws that beginners often miss. You have to preload them.
Yes. You can't just machine them when they're relaxed.
No, you need to simulate the clamping force. You use a ring or a slug, clamp down on it with the force you'll use on the part, and then you bore the jaws.
And that compensates for what's called jaw lift, right? You're machining them in their stressed, clamped state.
You are. It's a little extra setup, but that's what delivers the highest possible accuracy.
And beyond accuracy, we have to talk about preventing damage. The marring and deformation.
This is the soft jaws insurance policy. It works on 2 principles. First, like we said, the jaw material is softer than the part.
So the jaw conforms, not the workpiece.
The second principle is force distribution. Hard jaws are 3 small points of super high pressure.
Like 3 little needles pushing in.
Exactly. But a soft jaw, bored to the part's profile, achieves full surface contact. You're spreading that clamping force over a much, much larger surface area.
So force divided by a large area equals low pressure. Instead of high pressure points, you get these large areas of low pressure.
And for a thin-walled part, that is everything. You try to clamp a delicate aluminum tube with hard jaws, you will crush it, you'll deform it instantly. With soft jaws, the pressure is so distributed you can hold it securely without any distortion.
You can often even get away with a lower overall clamping force, right?
Right.
Because the grip is so efficient.
Often, yes. Which further reduces any risk. They're just the versatile heroes for any part that isn't a simple, solid cylinder.
So what does this all boil down to? For you, the person listening, the machinist or engineer making this choice, let's synthesize it.
Okay. If the job involves raw material, needs massive torque, and you need it done fast with zero setup for a simple shape, you grab the hardened, serrated hard jaws, their power, their efficiency.
But if your job needs high concentricity for a second op, if it's a thin-walled part in a regular casting, or has a finished surface you cannot mar, You have to invest the time to machine a set of soft jaws.
It's a trade-off. It's not just about hardness, it's stability versus protection. It's setup time versus part quality.
And that brings us right back to that operational decision, the one that managers in high-volume shops have to make constantly. Setup time.
That time is the friction point. It's not free.
Right. It takes skilled labor and machine time to bore a set of soft jaws correctly. So that leaves us with a final thought for you to mull over.
Given that durability and zero setup time of hard jaws versus the absolutely essential protection and concentricity from soft jaws, how should a high-volume shop calculate the tipping point? At what point does the potential scrap rate or the cost of rework justify that extra hour of skilled labor to set up the perfect soft jaw profile?
Think about that calculation. Where does that tipping point lie for your shop, on your parts, for your bottom line? That's something to think about. We'll catch you on the next deep dive.